Hello, this is Dr. Liu. In this video, I will introduce projectile motion to you. So as you can see, here's a diagram. This diagram is from OpenStax, their college physics textbook. So I'm giving credit to them. Okay. And maybe moving that over here. Okay. So as we can see, here's a soccer ball player. He's kicking a ball, and the ball goes up at this parabola. And we can imagine that while in air, the ball traces this upside down parabola, which is a projectile motion's trajectory. So we can imagine there's no air resistance or air drag, although that would be no fun to play soccer ball without any air. You won't be able to do any tricks. This is an approximation. So we assume there's no air drag, so only gravity applies to the ball. So we have already been introduced to 2D kinematics, such as two-dimensional positions, velocities, and accelerations. So let's use that all introduction over here. So we start from this origin. This is the origin of our position. Let's just imagine that the ball was kicked at this exact position, and this player's right foot was just kind of following that trajectory, although the foot and the ball contact was already lost at the point, this origin, that makes the ball a projectile. As it's lost contact with the foot, it is only under gravity. So it's going here. We can see that this exact position is kind of an R0 at the origin. Here's a 0, and this one here will be the R1. So this is a 1, 2, 3, 4, and here's no ball. I don't know why. So here's 5. So the ball eventually gets over here and maybe starts going down further, but we don't really have the rest of the graph. So we have 5 different positions besides R0. So the vector-wise, I like to draw maybe not the R1 because that kind of overlaps with the velocity too much. So let's draw out R2. So starting from the origin, pointing to the center of the ball. Let's do it one more time. Man, that's worse than the previous. I think I have some parallax going on. Perfect. Okay, so this is R1, R2 vector, and this is R3 vector. It kind of overlaps too much, right? And R4 vector. So let's draw the R4 out. So this is R4, right? So these two and also this one, now we can call that R5. They represent how the position vector is changing. It points in different positions and with different distances from the origin. So those are the positions, and in between them, the change in position should indicate the velocity direction. Although we don't have the immediate R3, I can say, well, the velocity between R2 and R4, the change in position is from this to that. So with a different color, let's draw the change in position from this point to this point. So this is how the position changed. So this is delta R, say 2, 4, from 2 to 4, right? So from 2 to 4, the velocity must be pointing this way, kind of upward direction. And then from 4 to 5, the average velocity, the change in position is this. Kind of horizontal, but not necessarily horizontal. This is a delta R4, 5. So from 4 to 5. So the velocity will point in this direction, average velocity. Remember, average velocity doesn't tell you exactly what's going on at the instance. So this is on an average between this position, the ball was on an average moving to the right. So this is also the direction parallel to the average velocity between 4 and 5. This is also parallel to the average velocity between 2, 4, so kind of on its way up, right? So the velocity, if I draw it at this point, I think we went through this with graphical analysis. The velocity somehow is a tangent line with slope. So this is actually the same deal here. So our velocity should be tangential to the path. So if I draw velocity here at this point, I want it to be tangential to the path. So that's tangential to the red path. So this is v2. That's instantaneous, which means at the instance the ball is here, its velocity points up. And at this instant the ball is here, we should still draw a tangential line. I'll draw a slightly shorter one because I imagine the ball is reducing its velocity as it goes up. So this is v3. Okay, kind of crammed in there, so we'll move it down here, v3. Alright, so the v4 we have roughly this way. So slightly shorter v4. And as we come down, now the tangent line points a bit downward. This is v5. Okay, so the velocity keeps changing direction. On its way up, it kind of points up and forward. And then on its way down, it points downward and forward. And there's this special point at the top, only points to the right. So this is v max height. Oh, it's very long. Okay, only points to the right because it doesn't travel either up or down. Okay, so these are all the velocities. One thing I'm trying to do to maintain is this. See, the horizontal amount of velocity, which is the horizontal component of this vector. This is Vx at 2. And the horizontal velocity of this, Vx 3. And the horizontal velocity of this, Vx 4. And this whole thing is Vx max height, right? And here now on top, Vx5 or V5x, whichever version it is, it's fine. So what I'm showing here is the horizontal component somehow is constant because we assume there's no air drag, right? So the effect of gravity is only on the vertical axis, right? So I think I'll change my notation here a little. So max height x. So this is 5x. I think that's a little easier. 2x, 3x, and 4x. Okay, change my notation. So now the numbering is preceding the component. On the other hand, the y velocity, if I drew it out, it would be diminishing as it goes out, right? So let's move that velocity mark right here. So this will be the y velocity, v2y. And v3y is only this long, it's shorter. So I don't think I can mark it, but maybe I should point to it. v3y. And here's a tiny bit of v4y. v4y. And there's no vy anymore. And now v5y is downward. v5y. So as we go up, we have a large amount of vertical velocity that is getting less, getting zero, getting negative. So this feels like you are adding negative y velocity constantly, causing a positive y velocity to reduce to zero and proceed to become negative because you keep adding negative y velocity. That is a characteristic of a negative vertical acceleration, and that value, we know that already, is 9.8 negative, right? So the vertical motion in the projectile motion is exactly the same as the free-fall motion. There's no difference. The horizontal motion, on the other hand, is a constant velocity motion. Just keeps proceeding to the forward until the motion is stopped. Say the ball hits the ground, the grass. All right. So velocity-wise, acceleration-wise, I don't really have a lot of space for that. But since we already talked about it, the velocity keeps getting less and less. So the acceleration must be downward with a, acceleration. So is minus g in the in the y direction. Okay, so that's the same acceleration. That's the same acceleration. Even on top, see on top it cannot afford to not have acceleration, because if it doesn't have an acceleration, then it will not change its velocity. So it just go up and start going forward because it doesn't want to come down. It doesn't have a velocity downward, and it doesn't have acceleration to change that no downward velocity into a downward velocity, right? So the acceleration is a constantly downward thing. That's why it keeps reducing the velocity until it's zero and keep reducing it past zero. So here we still have a negative acceleration and even further down. So the acceleration is constant and downward pointing. All right, so where does that lead us in terms of problem solving? We have more parameters than we had before, right? So each one we had, there was this angle, right? There's an angle, there's another angle, this angle, right? There's zero angle, there's this negative angle, right? So let's have a list of parameters. So we have these r as positions, right? The positions can be decomposed into x and y's, right? These positions, this is x, or the rx, whichever you prefer. This is y, ry, let's use r2y, that means 2x, x2, something like that. Okay, so instead of position in x, initial position in x, now we have a set of two. So we have initial position in x, we have a final position in x. So initial position in x is a 0 right here in this example. The final position in x is very long, so this whole thing is x final position in our graph. So let's use that r5x or x5, right? So x and x0 and x. Now we also have y0 and a y. So the y0 in this case is 0. In other examples may not be 0. And y is this right here. So this height. So this height is y5 or r5y. All right. So we have a final and initial velocity as well. So we had v0v. So let's do that. So v0. So that will be the initial velocity pointing upward, and also there will be an initial velocity angle. So this is angle of the initial velocity. And then we'll have a final velocity v, and that is the final velocity pointing this way. Initial velocity, if you just drew the ball, this position is kind of following that red trajectory upward. So this is v0, right? Initial velocity tangential to the red curve. All right, so final velocity and also final velocity is angle, which is this one here, so theta 5 in this case. And we also have theta 4. Oh, it's really getting busy here. Let's do theta 2 and skip the theta 3. There's no space for it. Maybe if I squeeze. Okay. Okay. Good. All right. And then what else? We have a fixed acceleration, so we skip that, and then we arrive at time t. So these are the parameters. 2 positions for x, 2 positions for y, initial, final, And the velocity has initial magnitude angle and final magnitude angle. And these two can be replaced by a v initial x and a v initial y, because this is our rule. We have a vector velocity which has a magnitude and angle. We can also have the same thing with an x and y component, right? So they represent the same thing. This can also be replaced with a vx and also a vy, except that vx is the same as v initial x, because there's no acceleration in x. So right, ax is 0, so x velocity does not change. Like I was drawing, horizontal forward, the same exact amount everywhere horizontally. So that's basically just that. And this reduces to the one less amount of unknown. So if you want a list, here's a list here. So alternative list, copy, paste. Okay, so what I want here is I want a list, right? Just like in the previous time, I had a list. So I would have initial positions in x and y, final position in x and y, initial velocity in x and y, and then I don't have to have a final velocity in x, because that's the same as initial velocity of x. So I just need the final velocity of y, and the angle then can be calculated with a known final velocity in x. And then I also need the time over here. So now I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 parameters. This is a larger problem to solve than in the previous time with 1D. Alright, so what kind of equation do we have? Well, we had the equation in 1D that solves the free fall. So we'll adapt to that. On the other hand, we want to use y for the motion. The x will be just for the horizontal. So the equations look like this. X is x0 plus v0x times t, because this is that's not good, a constant velocity motion in x. There's nothing affecting the horizontal motion. In y, now this is a rewritten version of the original freefall problem. So v0y t minus 1/2 gt squared. This all looks familiar. Initial x, final x, now we use y components, right? And initial v0 velocity, now we need to specify v0y. This v0y, this y here is very important. So let's do some emphasis right here, and some emphasis over here. X and y. Oh, see that? That just red keeps going behind the black. Okay. So now we also have the vy equals v0y minus gt. So this is our system of 3 equations, and this one's constant velocity motion in x. This is constant acceleration motion in y. Acceleration motion in y. So that's how this thing works out. We have 3 equations, and there's x follows this, y follows this, and velocity y follows this. So a lot of times we were given initial conditions like these. We knew how fast we were kicking the ball and at what angle we kicked the ball. So we didn't really know this, and we have to do some decompositions. So we're given there, better dot. So we're given initial velocity and the angle initial. So we need x and y initial velocity so that we can use them here. Oh, also here, let's also highlight that with red. Okay, just keep going to the background. Okay, so how do we do that? Yeah, well, these are vector, magnitude, and angle. To get these components is really easy. V0x is V0 cosine theta 0. V0y is V0 sine theta 0. So we need to do this before we start the problem solving, because we need these values, right? We need these. So we get these, and then so now say solve problem, and got Vy. So then what is V final, and also is angle? Well, we just do it in the reverse way. So now we have component Vy, and realize Vx hasn't changed. Same thing as the initial x, right? We can borrow it from here. So now V is Vx squared plus Vy squared, which is the same as V initial x squared plus V, not initial y squared though. This is talking about the final, right? So not initial, there's a square. And the angle, this is final angle, is tangent minus 1 Vy over Vx. So unless we have set it up really awkwardly that the initial velocity points backwards with a negative, this will never be negative. But still, we want to be all-inclusive, right? So this is adding 180 degrees only if Vx somehow is negative. That means you just set up the x-axis pointing the other direction. That will be really awkward. I'll have trouble solving problems like that, just because I tend to think forwardly. All right. So anyway, this is kind of the flow of the problem. You'll be looking for all these parameters. So you'll be looking for all these parameters. And once you have these parameters, maybe some of them are actually given in these magnitude and angle way. You break them down, and once you have everything, you can solve the problem. And once you solve the problem, realize that you maybe ask for these that are not component ways, so you combine the component to get these answers out. Thank you.